Hello, everyone, and welcome back to The Explainer. I am absolutely thrilled to have you with us today because we are looking at something literally mind-bending. We're diving deep into the water technology of ancient Sri Lanka, specifically looking at the incredible engineering feats you'd find covered in a grade 8 history class. You know, when we think of the ancient world, we usually picture giant pyramids or massive stone walls, right? But today, we're looking at a civilization that mastered the very lifeblood of our planet, water. So let's jump right in and uncover this masterful ancient engineering.
I want you to really think about this question for a second. Imagine standing in a dry, completely arid landscape thousands of years ago. You don't have computers, you don't have lasers, heavy earth-moving machinery, or any modern surveying equipment whatsoever. Yet somehow you are tasked with capturing monsoon rains and moving that water across dozens of miles to feed an exploding population. I mean, how did ancient engineers move water for miles with that kind of pinpoint precision? It is a puzzle that still leaves modern hydrologists completely in awe, and we're going to piece it together right now.
So here's our blueprint for today. We're going to start with survival in the dry zone, then move into the era of giant tanks and take a look under the hood with the anatomy of a tank. After that, we'll trace the giant canals, and finally cool off by looking at ancient ponds and filters. We've got a ton of fascinating ground to cover. All right, Section 1, Survival in the Dry Zone. Let's talk about the earliest villages. Long before the era of Christ, the very first settlements in Sri Lanka popped up in the dry zone. Now, if you're living somewhere where it downpours for just a few months and then stays bone dry for the rest of the year, water isn't just a resource, it is absolute survival. To grow food, these early villagers had to figure out how to catch the rain and hold on to it. So we actually see a clear evolution here based on pure necessity. Early on, you had what were called village tanks. These were pretty small-scale reservoirs built by local families working together under a village headman. Very localized, modest solutions. But as we hit the 3rd century BC, the population just absolutely exploded. Small village tanks simply weren't going to cut it anymore. That's when we see the rise of the giant tanks. This required serious royal patronage, kings who could command the massive labor forces needed. Early examples built during the reign of King Pandu Kavaya include Jayavapi and Abhayavapi, which we actually believe is the present-day Basawakulama tank. This massive shift from community-led to royal-led infrastructure changed their landscape forever.
Moving on to Section 2, the era of giant tanks. This is where the master builders enter the picture.
This era was not just about making bigger puddles of water. It was about totally transforming the economic and agricultural capacity of an entire civilization. Let's trace this timeline. Like we said, pre-3rd century BC was all about those small village tanks. But the real game-changer hit between 67 and 111 AD with King Vasabha. He was the very first to initiate truly large-scale tank construction. He built 11 big tanks, including what we now call Mahavalachia Weva. Fast forward a bit to 274 AD, to the reign of King Mahasen. This guy was an absolute visionary. The historical chronicles record that he constructed a staggering 1,000 tanks. 1,000. His crowning achievement was the massive Minaria Weva. The sheer scale of what he accomplished was so impactful that the people literally deified him. He became known as Minaria Devio, the god of Minaria.
Let's just pause and think about what building these giant tanks actually entailed. They weren't just digging big holes in the ground. They were finding narrow river valleys flanked by mountains and then constructing earthen dams, some 30 to 40 feet high, stretching for several miles across the valley. Just imagine deploying thousands of workers for years, moving tons of earth purely by hand and animal power. And actually, it gets crazier, because they had to understand the geology perfectly so the subsoil wouldn't just absorb all the water. Plus, they had to pack the earth so densely that it wouldn't immediately burst under the insane water pressure. The logistical and geological genius required here is just staggering.
All right, Section 3, Anatomy of a Tank. Let's look at the brilliant inventions that made this possible.
So how did these huge earthen dams hold up without failing? Let's look under the hood. First up, we have the sluice. A sluice is basically an engineered gate or channel to let water out of the tank in a highly controlled way. The ancient engineers actually built bottom sluices right at the tank's bed, which let them drain the whole tank and, crucially, flush out the accumulated mud and silt. Then they built upper sluices a bit higher up for the regular daily water release. But here's the catch. Opening a gate at the very bottom of a massive tank is incredibly dangerous because the water pressure down there is just massive.
To solve that dangerous pressure problem, they came up with one of the most brilliant engineering marvels of the ancient world, the Bisikotua. You'll also hear it called a cistern sluice.
The Bisakotua is a uniquely Sri Lankan invention. It's this square-shaped structure built inside the tank, right near the dam. Before water is ever released into the main outlet tunnel, it has to enter the Bisakotua first. Inside, there are regulating doors. By forcing the water into this square chamber, it absorbs and dissipates all that chaotic, destructive pressure of the deep water. Only then is it safely released outward. Without this pressure regulator, opening a sluice would literally tear the earthen dam apart from the inside out.
If you look right here on screen, you can see how a modernly maintained Bisakotua sits right out in the water on a large tank. Beneath the surface, that structure is taking the massive, crushing force of the reservoir and totally taming it, allowing humans to safely draw the water they need to survive. It is a true testament to their deep, deep understanding of hydrodynamics.
But water pressure isn't the only enemy of a dirt dam, right? Think about what happens on the surface when the wind blows across miles and miles of open water. You get waves. Unceasing, relentless waves crashing against a wall of dirt. Over time, that dirt is just going to wash away. So their ancient solution? The breakwater. This was a thick, highly protective layer of stones laid specifically on the inner, water-facing surface of the dam.
Take a look at these tightly packed, jagged rocks here. They basically serve as the dam's armor. When the waves hit this rock face, their energy gets entirely broken up and absorbed, protecting that vulnerable earthen core underneath. It's a beautifully simple but incredibly effective piece of engineering that has literally allowed some of these dams to survive for over 2 millennia.
Now let's talk about flow management. A tank obviously needs to take water in, and it desperately needs a way to get rid of too much water. For this, they built spills. The inner spill brings external water into the tank from rivers or canals. But the genius part here is they built a small pit right at the inner spill. When outside water flows in, it drops its heavy silt and mud into this pit before it even enters the main tank. When the water flow stopped, workers could just dig the mud right out of the pit, which saved the entire massive tank from filling up with silt. Super clever. And on the flip side, the outer spill acts as a safety valve. It safely releases excess water during massive monsoons so the dam wouldn't overtop and totally collapse.
All right, moving to Section 4, Engineering the Giant Canals. This is where we see the vast water grids.
So we have massive tanks storing millions of gallons of water safely. Great. But how do we get that water to the distant farmlands? Ancient Sri Lanka didn't just build localized systems, they built these vast, interconnected water grids. We have the Elahera Ella, constructed by King Mahasan, stretching 30 miles from the Ambanganga to the north. Then we have the absolute giant, Jayaganga, sometimes called Yoda Ella. Built by King Datu Sena, it carried water from Kalaweva to Thisaweva in Anuradhapura. This thing is an astounding 54 miles long, and in some places up to 40 feet wide. Later on, King Agabodi I constructed the Minape Ella, drawing from the mighty Mahaweli River. These canals were basically the ancient equivalent of our modern interstate highway systems, just for water.
But to make water flow smoothly over 54 miles without it rushing too fast and eroding the banks, or without it just stopping entirely, you need a perfect, incredibly subtle slope. Which brings us to this staggering number: 1 inch per mile.
The Jayaganga Canal maintained a precise, almost invisible gradient of just 1 single inch per mile over its first 17 miles. Let that sink in for a second. Without any modern surveying tools, without satellites, without laser levels, these ancient surveyors mapped a path across rugged, varying terrain that dropped precisely 1 inch for every 5,280 feet of length. This classic example proves, without a doubt, that the ancient Lankans were absolute masters of land surveying and geographical engineering. They knew exactly how to measure and read the Earth with a precision that honestly defies belief.
Finally, Section 5, Ancient Ponds and Filters, the role of water in daily life and religion.
Because, water wasn't just for agriculture, it was deeply woven into the fabric of daily life, religion, and the royal courts. Ponds in ancient Sri Lanka were constructed by digging into the earth or building stone walls right on rock plains, and they fulfilled a whole variety of specialized needs. You have the colossal 8th Bakuna in Abhayagirya, which was likely used for bathing. Then there are the royal water gardens of Ranmasu Uyana, and we absolutely can't forget Sigiriya with its natural pressure fountains. Those were utilized for aesthetics and royal water sports. And then we have the famous twin ponds in Anuradhapura. These served a triple purpose, providing drinking water for the bhikkhus, or monks, adding immense beauty to the monastery, and acting as a natural air conditioner, cooling the surrounding environment.
Take a look right here.
You can see the breathtaking twin ponds on the left, with their beautifully carved stone steps. And right beside them, on the right, there's a square structure that is way more than just decoration. This is a highly sophisticated multi-stage water filtration system designed specifically to ensure the water entering those twin ponds was perfectly clean. Here is exactly how this ancient filter operated. Step 1. Rainwater and surface water first collect in the outer compartment, which basically allows all the heavy debris to settle to the bottom. Step 2. As the water level naturally rises, it is forced to flow over 6 precisely carved cuts on the top of the middle stone wall. This acts as a secondary mechanical filter, aerating the water and leaving even more impurities behind in the inner compartment. Step 3. The newly filtered, totally clean water finally flows through a designated pipe directly into the pristine main pond. It is just a stunning display of functional, elegant design.
Which leaves us with this final thought. Today, we've seen a civilization that scaled from small village tanks to colossal reservoirs. We've seen the invention of the Bissocatua pressure regulator, a 54-mile canal sloping perfectly at 1 inch per mile, and beautiful, elegant stone water filters. So, the question I want to leave you with is this. If an ancient civilization, working entirely with stone, earth, and human ingenuity, could invent such perfect, harmonious, and sustainable solutions for their environment, what brilliant solutions are we perhaps missing today? Thank you so much for exploring the water technology of ancient Sri Lanka with me on The Explainer. Keep learning, and I'll catch you all next time.